So let's look at the following example. We have a curve C described by this vector valued function, and the ultimate goal is going to be to find the equation of a tangent line at a point, and we're going to do t equals 1. But before we actually start doing some computations, let's look at what this curve actually looks like, and I'll show you why looking for a tangent line for a curve in 3 space really is not any conceptually different than what we've been doing all along. Okay, so here is the graph of our vector valued function, and we're going to look at this when t is equal to 1. So when t is equal to 1, we're at 1, 0, 1, which is about right here on that curve. And just to show you that there's really nothing different about conceptually how we find this tangent line, what we can do is we can look at another point on the curve that corresponds to a slightly different t-value. So those are really just 2 points in space, and anytime we have 2 points in space, we can draw a line between them, right? So we can draw a secant line to the curve. And we can note, this doesn't really look that different than what happens in R2. How do we find a tangent line? Well, we talked about you just let t be closer to 1. You find a point on the curve that corresponds to that. And once again, 2 points. Determine the equation of a line, and that looks much closer to the actual tangent line to the curve. So the conceptual construction of this tangent line is the same as it's always been. We just have to figure out how to find it and describe it in terms of the vector valued functions that we're looking at now. All right, so we've seen this curve C, and hopefully I've convinced you that conceptually how we construct the tangent line is the same thing that we've always been doing. Well, now we actually want to find a vector valued function that will describe this tangent line at t equals 1. So how do we do that? Well, all we're really trying to do is find the equation of a line. And to find the equation of a line, we need to find a vector parallel to the line, and we need to find a point on the line. So let's start with the vector first. To find a vector parallel to the line, what's a good choice? Well, we know that r prime of 1 serves precisely as a candidate for this vector v, so let's compute r prime of 1. So we'll have to compute r prime of 1. And in order to compute r prime of 1, all we really have to do is compute r prime of t first, and then just plug in 1. So in order to do that, finding the derivative of a vector valued function is quite easy. All we have to do is take the derivative of each component. So we first have to differentiate cosine of 5t. So when we take the derivative of cosine, we get a minus sign. But we have to remember, since it's a cosine of 5t, we have to take the derivative of 5t. So we get a minus 5 sine 5t for that first component. Similarly, for the second component, we'll get a 5 cosine of 5t. And differentiating the z component here is very, very easy. So that's our vector r prime of t. And our vector v parallel to the tangent line is going to be r prime of 1. So all we have to do is plug in 1. So we get minus 5 sine of 1 times 5 cosine of 1 times 5, 2. And sine and cosine of 5, they're not nice numbers, but they're just numbers. Doesn't matter. So our vector v that we're going to use is just minus 5 sine 5, 5 cosine 5, 2. So we'll keep track of that and find the point. Okay, so now we have to find a point on the actual tangent line. And in order to do that, we're going to use the fact that the tangent line and the actual curve have to agree at the point of tangency. So we can use r of 1 to find a point on the line. So we can find a point on the line using r of 1. So our P0 will just be R of 1. And we obtain that by just plugging t equals 1 into our original function R of t. So this was cosine of 5t, so that'll be cosine of 5. Y component was sine of 5t, so this will just be sine of 5. And the z component was t squared, which will just be 1. Now we're in a position to find a description of this tangent line. And remember, the tangent line is just a line. In order to find the equation of a line here, we can just take a vector parallel to the line and a point on the line and make it this way. We found that our v here was minus 5 sine 5, 5 cosine 5, 1. And we just found that our P0 was cosine of 5, sine 5, 1. And so what I want you to take out of this is that finding the equation of a tangent line is the same as finding the equation of any line here. We need a vector that's parallel to the line, and we need a point that's on the line. We find the vector parallel to the line here by taking r prime of 1. We find our point P0 by requiring that the tangent line and the curve agree at the point of tangency, and we can just find that by evaluating the original vector valued function at t equals 1. And then we just find the equation of the line the same way that we've done before.